Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to continue our conversation about acids and bases by talking about that ubiquitous of topics, pH. So when we're looking at acid and base chemistry, one of the big things we're going to be looking at is the amount of protons or hydronium molecules that are essentially present in a solution. So whether, depending on your resource, some resources are going to be very deliberate about calling these protons, and some are going to be very deliberate about hydronium. Hydronium is a little bit more accurate, but it is worth noting that due to the older Arrhenius base notation, protons is far more ubiquitous. And so it is worth noting that a lot of these resources are going to make use of this older Arrhenius nomenclature. However, we're going to try and use these pretty interchangeably. So let's go ahead and look at those free protons. So let's say I have something like HCl releasing protons freely into the environment. Well, it turns out that these proton concentrations can very easily go anywhere from 10 molar if I've got 10 molar HCl, which completely falls apart, to anywhere down to 10 to the negative 15 molar if I've got a lot of hydroxide. So we have a very difficult time trying to describe a solution that can vary over 17 orders of or 16 orders of magnitude. That's a lot of magnitude. And so as a result, whenever you have numbers that go over such a big range, it's very common to use a log scale. And one of the more common notations is, especially if it's a log going to smaller and smaller values, is to use what's called a p notation. So p is going to be a prefactor. And so if you put p in front of some sort of number, it just means I'm taking the negative log of that number. So p of anything is going to be the negative log of that thing. So we're going to be looking at pH. So this would be the negative log of H, or proton. So this is really where that pH nomenclature comes from. So as you'll notice, it's based on the older Arrhenius nomenclature, but it can also be used to refer to the negative log of hydronium. And you can do pH or P of anything, including, say, the concentration of fish, where it would be the negative log of the concentration of fish. You name it, you can take a negative log of it, and we probably will. However, just as a quick reminder, because it's very common to refer to the hydronium concentration as pH, if we need to get that concentration back out, it's just 10 to the negative power. Conversely, if you're looking at a hydronium concentration and you want to try and figure out the pH, first thing you're going to want to look at is what's the exponent. That exponent is going to roughly be the pH of the solution. So keeping an eye on exponents is going to be really useful as we walk through these solutions. Now, one of the problems is that because hydronium and hydroxide can end up reacting with each other, this means that it turns out the amount of hydronium and hydroxide are going to be linked via our Kw. So as hydroxide goes up, hydronium will go down. As hydronium goes up, hydroxide goes down. And so we're going to be looking at how this, how these two species relate. However, what we can do is knowing that the product of these has to be 10 to the 14th, I can find the hydroxide calculation under any set of conditions just by taking 10 to the negative 14th divided by the concentration of hydronium. Now, it turns out that if we're looking at something like pure water, it has a very special concentration. So if I've got pure water, the hydronium concentration is going to be 10 to the negative 7th. And then 10 to the negative 14th divided by 10 to the negative 7th is 10 to the negative 7th. So if I've got pure water, I have equal amounts of hydronium and hydroxide. This is what we call a neutral solution, where we've got about the same amount of acid and base. So specifically hydronium and hydroxide. We can also do this in the P notation, where the pH would be 7. And so this is why we say a pH of 7 is neutral. However, one of the things we run into is that because the hydronium concentration can go from 1 molar to 10 to the negative 14th molar, it means it's also going to be very common for the hydroxide concentration to do the same thing, but in opposite directions. If I have a hydronium concentration that's 1 molar, my hydroxide is 10 to the negative 14th. If I have a hydronium concentration of 10 to the negative 14th, well, my hydroxide is 1 molar because, again, that interplay of Kw. So as a result, we're often going to refer to OH concentrations also using a log scale, but instead of pH, it's going to be pOH. So this is just going to be the negative log of, because we're ever so clever, OH, or hydroxide. Now, one of the really cool features here is that because protons and hydroxide is linked, so will pH and pOH. So we can start with our water dissociation constant and then have some fun with logs. We can take the negative log of our 10 to the negative 14, so our Kw. Then if I take the negative log of the right-hand side, I also have to take the negative log of the left-hand side. And then I can make use of some fun log laws. So the log of a product is the same as the sum of the logs. So if I've got log of protons times hydroxide, this will be the same thing as negative log of protons minus log of hydroxide. Now we can have fun because negative log of 10 to the negative 14th will just be 14, and that's pH and that's pOH. So it turns out that pH plus pOH will give you 14 under room temperature conditions. Again, Kw can change with temperature. And one of the things that this does is help illustrate that as the pH increases, so as the system has less protons, the pOH will decrease. In other words, it will gain hydroxide. And so this helps show that relationship in between protons and hydroxide. And so we can go ahead and take a look at the kind of broader scale. So if I've got a hydronium concentration of 0, this means I'm going to have a 1. This means I have a pH of 0 because 1 is the same as 10 to the negative 0. And this is going to be very acidic. I have to have a lot of acids disassociating to release that many free protons. However, if the hydronium is going to be, or the pH is 0, this means that my pOH will be 14. So again, these will end up being linked. If I'm neutral, this means both hydronium and hydroxide are 10 to the negative 7th, which means pH and pOH are both 7. So this makes the neutral a quite special point. However, on the other side, if I have a very basic solution, I have a lot of hydroxide, like 1 molar hydroxide, well, that means I've got a pOH of 0 and a pH of 14. So this really helps illustrate kind of the range of objects. Quite acidic over here, quite basic over here. However, because we now have these 4 different metrics, it can be a little hard trying to keep them straight and interconvert. So one of the ways I like illustrating this is using an equation square or a conversion square. So I can convert from any one concentration to any other concentration by using the equations that I know to relate each of these pairs. So for example, if I know the proton concentration, I can find the hydroxide concentration simply by knowing that their product equals 10 to the negative 14th. So easy to calculate one or the other. Similarly, as we just illustrated, pH and pOH gives you 14. So if I know one, I just do 14 minus that to get the other. Now, the up and down portions can be a little tricky because I can turn my proton concentration to hydroxide, or I can turn it into pH by taking the negative log, or I can take that pH and turn it back into protons by doing 10 to the negative pH. Similarly, the hydroxide can be used to determine pOH, or the OH can be determined from pOH. So as long as you knew one, you can walk through and find any other just by walking around the square in whatever way is the most convenient for you. So next time, we're going to be looking in a little bit more detail of how we can produce these protons and hydroxide groups by looking at acids. Until then, take care.